Okay, so today we have the block of fluid dynamics. So we will, as you can see here, we will speak about these main topics, just some basics. What do we understand concerning fluid dynamics? We will keep there at continuum mechanics and what are the prerequisites for this. And then the main equations, which are the conservation equations of mass and momentum. And as you know, these equations are not enough in order to have enough equations for all the unknowns. So we also need constitutive equations to describe the constitutive behavior within fluids. And then we will go towards acoustic, because we all know that within the full set of compressible flow equations, we already also have wave propagation. So we already also described their acoustic fields, but it's very difficult to decompose such compressible results as the pressure or the velocity or the density into the fluid dynamic part, which we mainly call the vortical part because we have vorticities there, and the longitudinal part, which is a part of the compressible quantity, which will go towards acoustics. Okay, so when I'm speaking from continuum mechanics, then the most important quantity there is the Knudsen number. And the Knudsen number is the ratio of the free particle lengths and the characteristic lengths. And if you look here to this graph, you see here along this axis, there is a control volume. And on this axis, it's the density. And you see that when we approach to a control volume, which is getting larger and larger, we come up here to a more or less constant value for the density, which is clearly not constant because we will have variation in space and time, but it is then just at a scale where we have small fluctuations, which we then can describe by the continuum theory. And that is what we are considering on, and you see still at about 10 to the power of minus 18, which is very small, we can say, will we approach here to values which we can describe here by continuum mechanics. So we have enough particles there and can then have a state variable density as shown here, which is a continuous function of space. So x is the space coordinates. We will mainly use Cartesian coordinates. It's easier. So we have a x, y, and z component, and clearly it will depend on time. Yeah, and that makes it that we are in a 4-dimensional space, 3 space coordinates and 1 time coordinate. So if we are within continuum mechanics, then I just make it here explicitly, and let's do it here for the density. So as we had before, the density is a function of the space coordinates, which we explicitly write with x, y, and z, and the temperature. And the vector x will be the components x, y, and z. And what we are always looking for if we have physical fields is what is the total change of a physical quantity you have there. And the total change is written here with this symbol d. So d rho is the total change of the density. Now the density is a function, as we can see here, of the space coordinates and time, which means when you look for the total change, it's the change with respect to time and then dt, total change of time, plus the change, which is here again a partial derivative. So very important, yeah. This sine d means always it's the partial derivative. So it is really just a derivative on the coordinate as we have here x and the total change of this coordinate. The same here for the second coordinate and for the third coordinate. Yeah. So you see, since we will also use index notation, we should also rewrite our x vector as x1, x2, and x3. So we will somehow interchange between x, y, and z, where x is always for us x1, y, x2, and z, x3. Okay, now if we divide our equation as written here by the total change of the time, we get this total derivative of the function rho, which is for us the density, it's a scalar function, with respect to time. And that gives you, as you can see when we divide it, it gives us, as shown here, the change with respect to time. And then we see here the change with respect to the x1 coordinate. And now since we have divided by dt, we have here this term, which is the total change of the first coordinate with respect to time. And we have it also here for the second coordinate and for the third coordinate. And that we know is nothing else as the three velocity components. Yeah? And that is why we can write it now in such an index notation where we write here still the sum, and in the next step we just neglect the sum, because in index notation it is then just a derivative of the function with respect to xi, and we know xi takes, so I takes on the values 1, 2, and 3, so that it is the x1 coordinate, x2 coordinate, x3 coordinate, and the total change of the coordinates we have there with respect to time are then the components of our velocity. Okay, so what we should also consider is that what we have derived here, which we have named with the small d, in literature is very often then used with the capital T to really say it is the substantial derivative. And this is an operator which gives us the partial derivative with respect to time, and as we call this convective term. And this symbol here is the nabla operator. Do you know about the nabla operator? Or is this something new for you? I don't know if how you had the courses in fluid dynamics just with index notation, or you also used vector operators as the nabla operator.
We use both of them.
Yes, that's great. I think to use both is great because sometimes it's really easier to use the classical, let's say, vector notation and use the nabla operator, but sometimes I think it's really easier to have, as written here, such an index notation, because what is the gradient of a vector? Yeah, okay, we know it's a tensor of second order because tensor of first order is a vector, tensor of zero order is a scalar, tensor of second order is a kind of a 3x3 matrix, but clearly has other very important properties. So a tensor is a matrix, but not each matrix is a tensor. And within index notation, we will come to this also on the next slides. I think it's easier to remember. Yeah. So, but we could also here now rewrite this as d dt plus vi in sorry, this indent. Yeah, the dot for me is always that there is a scalar product. We clearly don't need it when we have index notation because it's VID dxi would be then written in index notation. What is important for us is to define which spatial reference system we are using. I guess you have already heard it. There is a Lagrangian frame and there is a Eulerian frame. So the Lagrangian frame is mainly used in computational structural mechanics, where the observer monitors the trajectory in space of each material point, and you are going with the deformations, yeah, as an observer. On the other hand, the Eulerian frame is, for example, you have a fixed position and you look down to the river where a boat is going over the river. So in this sense, then it is a Eulerian framework, and that makes sense for fluid dynamics because we are observing how the fluid particles go along the flow. However, very often we have coupled field problems. So we are interested in fluid structural interaction. So as I have told you, we will have this Lagrangian frame within structural mechanics, the Eulerian frame within fluid dynamics. And then what the standard way is that you introduce a new frame, you call it the arbitrary Lagrangian Eulerian system or frame, which couples these two standard Lagrangian Eulerian frame, and that is the frame you are using when you are dealing with fluid structure interactions. And we will keep the Eulerian frame because it's the appropriate frame for fluid dynamics, and that will be also the appropriate frame for acoustics. Okay, in the different frames, we have to look what are the total derivatives, yeah, of a general quantity, a general tensor. When we have a scalar, it's a tensor of zero order. And you see for the Lagrangian frame, and that is important to realize, it is just a partial derivative we have here. And we evaluate it at this capital X, which are the coordinates in a Lagrangian frame. In the Eulerian frame, we always have the small x as the position vectors. And as you can see here, we have exactly what we have derived for the density just 2 slides before. We have the local change with respect to time and the local change with respect to space, which is, as you can see here, connected with the velocity, and we call it the convective change. If you would combine now these two in a fluid structure interaction description, then we would come up to this one, where we again have clearly a convective change. We call this the convective velocity, which is just the difference between the velocity we have in our system and so-called, we call it already a grid velocity. Yeah, because when you think for a ventilator, then the rotor is rotating. And when you have a fluid structure interaction there, then the importance in the arbitrary Lagrangian Eulerian system is the difference between the velocity you have there and the rigid body motion of the rotor, which is then already called the grid velocity, because at the end we use any numerical discretization scheme, and there we have to move the grid we have within the rotor from time step to time step according to the rotational speed we have. Okay, so this is something perhaps you already have heard. We will not need all the details here. What we will need is, as I have told here, the Eulerian frame of reference. But as far as we already are interested in the noise being generated of a rotating system like a ventilator, we have to couple then the stationary parts with the rotating parts within the fluid dynamics simulation. And then you already need this arbitrary Lagrangian Euler formulation for computing the flow there. And perhaps you also take into account the fluid structure interaction according to the fluid forces on the structure, and then the change of the geometry within the fluid domain. Okay, so vector analysis is quite important, and I guess you are very well prepared, since I have heard that you use both notations. Just a small summary here, I think makes sense. When you are within classical vector analysis, we always teach the students, and I don't know how you have heard it, well, the gradient you just can take from a scalar. Yes, this is true for standard vector analysis, but actually a general description is done with tensor analysis. And we already will need in fluid dynamics, and I think you know it, you already had the course in fluid dynamics, the gradient of a vector. So this is a very restricted restriction when you just consider vector analysis. But we will extend it a little bit without going in too much details towards tensor analysis. So when we look here to standard vector analysis, then as I have told you, this nabla actually is a vector operator, and I write it down here for Cartesian coordinates. So it is the partial derivative with respect to x, and you get the x component. You take the partial derivative with respect to y, and you get the y component, and you do the same for the z, and you get the z component, which means simply if you have now here the following, that we take the gradient of the density, we take the partial derivatives of the scalar function with respect to x, of the scalar function with respect to y, and of the scalar function with respect to z. And you see, from a tensor of zero order, which is the density, it's a scalar, we get a tensor of first order, which is a classical vector. And I guess you know, what does this mean, the gradient of a scalar function? It shows us the strongest increase of this scalar function, in which direction it is, because you see, we get out here a vector. On the other hand, a divergence of a general tensor always reduces the order of the tensor. Now, the divergence as we have here of a vector means that we have here, I should write it a little bit more precise. I again write it here as a vector, our nabla operator in Cartesian coordinates, and we apply it with a dot product, which is a scale product, to our three components of a classical vector in Cartesian coordinates, the x, y, and z component. Yeah, and as we know, what we get out is then it would be just as a scalar product between two standard vectors, but one of the vector, as we have here, is a differential operator. We call it the nabla operator. So what we get out is we take the y component with respect to x plus the x component with respect to x, the y component with respect to y, and the z component with respect to z. And as you can see, you could also write this in index notation. It is dvi dx. Yeah, that would be quite, in this case, also simple to be written without all these special notations we need when we have classical vector analysis. Yeah, a little bit more difficult is the curl operator. So the curl of a vector we can also write it classically, yeah, as I have written it for the divergence, because we just write our operator with the three components, and then we know we have the cross product, and on the vector v, which is for us in fluid dynamics the velocity. The easiest way it is, so the order of your tensor will be the same. So we will also get out a tensor of first order, so a classical vector. I think the easiest way is to use it and write it with a determinant. So in the first line, we have the unit vectors in x, y, and z. The second one is the first vector, which was our nabla operator. And the last one is our vector, so the x, y, and z component. Yeah, and when we do this, we know we develop now along the first row, and that means, what do we have? We have this vector Ex, and then the subdeterminant, and the subdeterminant is exactly this part here. Yeah, so we have to take the partial derivative of the z component of v with respect to y minus the y component with respect to z. So as I write it here, it is dvz dy minus dvy dz. Minus, so you always have plus, minus, plus. Yeah? So we have, as you know, we have then minus the ey, the unit vector in y direction, and as a subdeterminant, we have this part and this part, yeah? Because you could also see it as you cancel out this row and this column, sorry, and this row. So we have here then the partial derivative of the z component with respect to x minus the y component of the vector, the x component of the vector v with respect to z. Okay, let's write it down. So we have dvz dx minus dvx dz. Yeah, and then we come to the last, which is here the unit vector in z direction, and this is our subdeterminant we have to compute. So simply writing down plus ez, and we take the derivative of the y component with respect to x minus the x component with respect to y. Okay, so these are the mathematical formulations. Let's see how we compute a gradient of a scalar, a divergence of a vector, and the curl of a vector. But we also have a lot of physical interpretation. I already have told you for the gradient. When we take the gradient of a scalar, then we know where we have the maximal increase of this scalar, in which direction it is. When you evaluate the divergence, yeah, and the divergence of a vector is not zero, then we know that we have there some sources or sinks, yeah, and that is exactly a scalar quantity, because the divergence gives a scalar. So if you have an equation like the divergence of a vector is equal to a scalar quantity, then this scalar quantity is the source or sink of this vector field. When you take the curl of this vector, then it is the vorticity, you have vorticity strengths of this vector. Yeah? So for example, as we know, the curl of a vector again gives a vector. So the vorticity itself, the vorticity strengths of this vector field, which is a so-called solenoidal field, is then again a vector. And we will have this very nicely in our equation, and we'll also discuss about a general decomposition of vector fields, which is very important in our case, because the classical flow has the vortical structures and are described by the curl of the velocity, which is the vorticity, and compressible parts are described by the divergence of the velocity. Yeah, we know we model an incompressible flow by setting the divergence of the velocity to 0, which means then for us we don't have any changes in the density. We assume the density to be constant and call such a case a compressible flow. Okay, do you have any questions or remarks, comments? Could be very interesting also for me from other courses. Or any questions?
I do not have any.
Okay.
So it was totally fine.
Okay, fine. That's great. Then we can go on if there are no questions. Yeah, and now we come to a very important theorem in fluid dynamics, but it's not only used in fluid dynamics, also in other physical fields. It's the Reynolds transport theorem. I think you already have heard about it. Have you had a detailed discussion on this theorem in a fluid dynamics course or other course?
I think yes, in the bachelor's and in the master's also.
Okay, so it will be just a small summary. So I think what is very important here is the sense that we are mainly interested, if we have a physical quantity, what is the total change? And the total change is written here. In our case, we have a scalar quantity, and we just have this relation between the small f and the capital F as written here. Yeah, you can imagine that would be exactly capital F the mass and small f the density. When you integrate the density over the volume, you get the total mass you have within a volume omega. So omega is for us always here the volume. And you are now interested in the total change of this physical quantity capital F, which is, for example, the mass. And you see, we can substitute this definition simply here. And so we integrate over this total quantity and then take this derivative, this substantial derivative. And as you can see here, in the Lagrangian system, as we already have discussed, well, this is simple as standing here. You take here a partial derivative of this quantity having any unit per cubic meter, a partial derivative of time, because the substantial derivative is just a partial derivative in the Lagrangian system. But in the Eulerian framework, we have to be careful because we know that the total change includes not only the partial derivative with respect to time, but we also have the convective term. And that makes sense that it has the following relation as shown here on these two lines, that we can take here the following, that we have this partial derivative with respect to time, and don't forget that this control volume may also change with time. And we have then a surface, and this is a closed surface. So actually we could also write here, I like it more, to take the partial omega as a function of t, which indicates it's the closed surface of the volume omega we have here. So this is also indicates then it's a closed surface. And we have here the surface enclosing this volume here. Yeah. So Sometimes it is also written, and we will also use here with this ring, and then it is clear it is a closed surface where we have to integrate over it. And for us, it is clear that what we have to take here is then in the surface integral, the scalar product between the velocity and the normal vector. So it is somehow the flux we have across our surface. So we not only have within the volume the local change with respect to time, but we also have to take into account the flux which is going in or out at the closing surface gamma, or let's call it the omega. And from here to here, we know that we can use the integral theorem of Gauss, which means that instead of this closed surface integral, we can rewrite it as a volume integral over the same volume omega, but we have to take the divergence of this quantity here of the integrand. So it is, our quantity is not only the velocity v, but also this scalar quantity we are interested for, this f here. Okay, so this is, as you already know, and now just a summary, this is now a very important relation for us in the Lorentz framework, because we describe our flow in this framework, that this total change can be also expressed by this relation here. And when we have a look now and already apply this theorem for the mass conservation, we know we have this relation here that we have to integrate the density over the volume to get the total mass. And we are interested in the change of the total mass. Yeah, and from physics, we know actually we have mass conservation, so the total change have to be zero. Please don't be confused when sometimes in books you see that this total change is different from zero, but that is then just a model where we already include some sources that the total change is not zero. This is a model. From physics, the total change has to be zero. Okay, so when we apply now Reynolds transport theorem, we see that we get this relation here now already very important for our flow velocity v and for our density rho. And since this has to be zero, we also can neglect the integral and get the local relations, which are the partial differential equation. And here we already have this important model assumption. This is our general case, and we call it a description of the fluid, which is the totally correct description of fluid, which is compressible. You will always have a compressibility, but to reduce the complexity, some fluids can be modeled to be incompressible. Yeah? And that makes sense because you see what you actually get is then a simple relation. And this is already a relation we have discussed, that the divergence of this vector is equal to zero. Do you know what is the impact on the physical field when the divergence of the velocity is zero? Which kind of physical field do we have? Had you ever a discussion about the so-called Helmholtz decomposition?
Maybe we called it in another way. I cannot remember.
Okay. So in this case, but we come to this Helmholtz decomposition. It means that you can decompose each vector field into a vertical field, which will be for us the classical flow structures, because we have vorticities there, and into a irrotational field, and the solenoidal field, yeah, which can be then described by the curl of a vector potential, the typical vortical structures, and the irrotational field can be described by a scalar potential, by the gradient of a scalar potential. For us from physics, what we now already get is when we look at this part and say that the velocity is zero, this index IC means incompressible, that this is a pure solenoidal field. That means you have no sources or sinks. Our field lines are closed field lines. This is typical for turbulent flow structures where you have all the vortical structures there, vorticities, and this is the so-called solenoidal vector field. Okay, so and sometimes, as I have told you before, you perhaps want to model some mass injection or something, and then you do not have here zero, you have here perhaps some term this somehow described by a scalar function which you have obtained by measurements or other computations, for example. But from the classical point of view, we have mass conservation, and so we always have zero. And that is very important that we see this is our general mass conservation, and that shows us we have a compressible fluid. For some cases, we can neglect the compressibility and we come up to an incompressible fluid. Do you know why a compressible fluid is necessary for wave propagation, for acoustic wave propagation? Do we also have waves within an incompressible fluid? Well, we will come up to this, and you will then really see if we describe our fluid as an incompressible one, we cannot have any wave propagation there. Yeah, so we just model classically our vortical structures. Okay, on the other hand, we have the very famous conservation of momentum. Momentum, as you know, the total momentum is the volume integral of the product between density and velocity as written here. And again, we are interested here in the total change of the momentum. And for this, we consider a small volume like a fluid particle, and we will now investigate how we can get there the conservation of our momentum, and that will be due to additional forces we can have on the surface of the body. What are the standard surface forces we have on fluids? Do you have an idea? There are already some symbols we have here. So here we have this P, and here we have tau. So P is the pressure. You know, a pressure is the force which is acting in normal direction on a surface, and tau are viscous forces, and they are acting as shear forces, so they are within the plane on which they are acting. Okay, and then clearly we could also have some external forces, which could be gravity, electromagnetic forces, whatever. Okay, so the local form is now as follows. We have written it down here, and I think you have discussed this already in detail in the fluid dynamics course, that we have here the time change of the momentum density, which is density multiplied by velocity. And we have this complex term here, not as easy, which we will also rewrite differently. And that is coming out due to the total change of the momentum, and that is balanced by the gradient of the pressure, the divergence of the viscosity tensor, we will also come to it, and we will need a model for these viscous forces, and any volume forces, which could be gravity, electromagnetic forces, whatever. And this here we call the dyadic product of two vectors. And I think that is really easier to be written in index notation, which you can find here on this line. And you see, actually, we have now two indices clearly, because tau is already a tensor of second order, so it has index I and j, and we have to take here the spatial derivative with respect to xj of this term here, and let I being constant. So where I takes on the value 1, and we get the first equation, and j is going on 1, 2, 3. Then we take I equal 2, we get the second equation, and then we take I equals 3, we have the third equation. So it is a partial differential equation, which is a vectorial partial differential equation. What we also introduce, I don't know if you also heard this within the fluid dynamics course, we introduced this momentum flux tensor that is a very appropriate way then to rewrite the fluid dynamics equations at a kind of a wave equation, which was done by Lytle within Aeroacoustics. And you see, we just include here the so-called, I guess you know it, the Reynolds part, which is written here, the pressure part and the viscosity part. And we should also introduce the fluid stress tensor, which consists of our pressure part and the viscosity part. Okay, so this is now just formally, and we will go to some details. So we have here now again written down the conservation of momentum in vector notation as written here, or I think easier as shown here in index notation. So it is a little bit rewritten. I have the derivation in the script. As you can see here, if we go back, this form you can see here is also called the conservative form of the conservation of momentum. But with the help of the mass conservation, you can rewrite it in the following form, that the density is then out of the partial derivative and also the density here out, which means we come up to this equation here, where we have our classical nonlinear term here, and we call this also in fluid dynamics the convective term here. Okay, so now I just go to show you a little bit how this is really easier when we go to this index notation. Well, I think all of you are trained what is the gradient of a scalar, but what is the gradient of a vector? Yeah, okay. I think in this case, we should go to index notation because it is dv I dxj. And the gradient, as we have already seen, for a scalar gives you a vector. So from tensor of 0 order, you come up to a tensor of first order, which means we increase by 1. the order is increased by 1. So that means the gradient then of a vector should give a tensor of second order. Yeah, and that is simply when we use index notation. So what we have here is dv1 dx1 dv1 dx2 and dv1 dx3. And now we take I equal 2, so we have dv2 dx1 dv2 dx2 and the second component partial derivative with x3. And the last line is dv3 dx1 dv3 dx2 and dv3 dx3. Okay, what you also see here that this is in the general case not symmetric, yeah? Because if we look here, then here we take the first component with respect to the second coordinate, and here the second component with respect to the first component. So it is not a symmetric tensor of second order. But you see, it's now really easier to compute it. And a second thing I want to show you is the following here, which we already also had in our equation. There was the divergence, and we write a second tensor with these brackets here of the viscosity tensor. And here it is clearly easier if you can write this in this form that you have here the index notation, so the viscosity tau ij with respect to xj. Yeah, and then what we already know, when you take the divergence of any tensor, you reduce the order by 1. So this is then d tau. And now I go to coordinates x1, x2, x3 because it's easier. So we have here always 1, 1 dx1 plus d tau 1, 2 dx2 plus the third component 1, 3 of the viscosity tensor with respect to the third coordinate. And that's the first component of our tensor of first order or classical vector. And in this way we go on. So we have here the component 2, 1 with respect to dx1 at the derivative of the component 2, 2 of the viscosity tensor with respect to x2 and t2, 3 with respect to x3. And then we have the tau 3, 1 with respect to x1 plus the component 3, 2 with respect to x2 and the component 3, 3 with respect to x3. Okay, so I think that should hopefully demonstrate you that this makes sense to use this index notation, and I'm very happy that I have heard that you interchange also in your other courses between this index notation, which is going towards, let's say, tensor notation, and the other one, which is our classical vector notation using this classical Nabla operator. Okay, so in this sense, now we can write explicitly our conservation of momentum with all this information. And we already introduce a first constitutive relation in fluid dynamics that we assume a Newtonian fluid to be able to express the viscous stress tensor by two material quantities which we have here. This is mu, which we also call the dynamic viscosity, and lambda, which is the bulk viscosity. And this is a simple tensor. I can write this down as a tensor. So this is the delta function. You know the delta function is equal to 1 if both indices are the same. So you have here this unit tensor or unit 3 by 3 matrix. You could also write it in this way. And we have here also the strain rate. And this is now very important to look here on. You see, you have once the derivative of the velocity with respect the I component with respect to xj and one the j component with respect to I, which means this here is a symmetric tensor. So this is symmetric. According to this definition. Yeah, and in a thermodynamic equilibrium state, we can express the bulk viscosity lambda by our dynamic viscosity mu, and we end up in this relation here, and you see that the unknown viscous tensor now can be described by the velocity itself. Yeah, it's the derivative of the velocities, and we have two material constants. For most cases, we can take it as constant, and even we can reduce it to one constant, which is the dynamic viscosity mu. Okay, the third equation, well, which is very involved, and that's nice that for most cases we can reduce it very simply, but especially if you are interested also in chemical processes, well, the energy equation is quite complicated. Here is a general form of the energy equation where we have E, this is the inner energy of your system, inner, sorry, energy. And you see what we actually have here is the inner energy and the kinetic energy in your fluid, and for this the total change. And you can see it is balanced here by different terms. One is the heat production term, which is here. The other one is the heat flux, the change of the heat flux, so heat conduction energy due to the heat flux, which we have here. Then the energy due to the surface pressure force, which in our case is here the derivative of the product between the pressure and the velocity here. So this is this term here. Then the surface shear forces, which we describe here by the viscosity tensor and the velocity. Yeah, and then clearly we can have it, for example, any mechanical energy by a force density and the dot product with the flow velocity. Okay, so I think again this equation in all details written down explicitly is easier when we have this index notation as you have here. Now the vector notation, yeah, you have to take care how to compute the divergences of the different thing, or a scalar product between a vector as shown here, the velocity, and the viscous stress tensor. Okay, we can reduce or simplify the conservation of energy. So in this case, in terms of the entropy as shown here, this is not as easy to be obtained, this equation. I have a derivation in my script. But what is important more for us, that especially when we are looking for aeroacoustics, we have flow in air, then we are in a thermodynamic state and we can describe it as adiabatic and isentropic. And then we don't have to consider any heat fluxes. We can neglect the viscosity of the fluid, which means you end up in this nice equation that the total change of S, which is the entropy, so this is our entropy is equal to 0. And if it is homoentropic, then you have a homogeneous fluid, and then we have simply this relation, which we can also write clearly as this is the same notation in this way with the substantial derivative operator capital T. And that will be also the case then for us when we will go towards aeroacoustics, that we will assume here a isentropic case and even simplify it for homoentropic fluids, which means our conservation of energy just tells us that the total change of the entropy is 0, which will have a very important impact on the relation between the density and the pressure. Okay, so do you have questions towards this part here? Perhaps a question from my side. Do you had in courses already very detailed discussion about this conservation of energy for any applications, where you really take also into account heat fluxes, for example, and get then also a further partial differential equation out of this conservation of energy for the temperature T?
We
Or
had
you
advanced
mainly... Yes?
thermodynamics. We had advanced thermodynamics, and I think we touched this.
Ah, yeah, okay. In thermodynamics, you have discussed it. Yeah, okay. Well, in fluid dynamics also you have to take into account this thermodynamics, and it's mainly this conservation of energy. It describes quite a lot, and we have to define the thermodynamic state exactly as you told. And then it can get very complicated for your fluid dynamics computations, because you have to take fully into account also the heating up of your fluid, and then have to consider this conservation of energy. And yeah, for some cases we can have then also simplified state equation where we at the end get rid of the entropy, and you get out of this equation a equation for the temperature T, where also the classical fluid dynamics quantities like the viscosity effects are also included in this case. Okay, in our case, we can really simplify it because we will just consider that there will be any generation of acoustic waves or flow around obstacles in air or flow through a structure. So we have confined flow through a pipe or whatever in this sense, and then consider this subset that more or less the temperature is constant. We get rid of the energy conservation because it is fulfilled. And as we will see soon, this has the impact then on the relation between the density and the pressure. Okay, and that is now the very important second constitutive equation we also need in fluid dynamics to get a relation between the pressure and the density. And we will still consider isentropic fluids, and there the speed of sound comes in. Actually, from the thermodynamic equilibrium, where we have that the total change of the entropy is 0, we use then a relation that we express the pressure as a function of the density and the entropy S, which simply means the total change as written here of the pressure is then the change of the pressure with respect to the density at constant entropy, total change of the density, plus the partial derivative, so the change of the pressure with respect to the entropy at constant density, and the total change of the entropy. And now you see, when we use this isentropic case, that the total change of the entropy is 0, we get here this very nice relation with the speed of sound c, here in a general form. It has not to be constant, it can change, be a function of space, that the total change of the pressure is equal to the total change of the density. That we can also write in our standard form in the Eulerian framework with the capital D, so dp dt is equal to c squared d rho dt. And I just want to remember that this substantial derivative is the partial with respect to time plus our velocity in nabla. Yeah? And that is a very general case where we also consider here in the isentropic case all these changes of the pressure and all these changes of the density. And we will even have further simplifications at the end, especially for acoustics, between the pressure and the density. But this here, for an isentropic case, we should consider then this relation that we have a substantial derivative of the pressure, which is directly proportional to the substantial derivative of the density by the value of the speed of sound squared. Okay, now we should also discuss about the dimensionless numbers. I think you know about them when you already had fluid dynamics course, because they are very important. And they are also very important for us in order to understand the different modellings of fluids, and also already in connection to acoustics. So the first important dimensional number is the Reynolds number. And the Reynolds number is for fluid dynamics one of the most important dimensional numbers, because you have a ratio of the inertial force to the viscous force. And that gives you a Reynolds number which is velocity times a length scale. So we have here a typical flow length scale. We take a characteristic flow velocity and divide it by the kinematic viscosity mu. And the kinematic viscosity is nothing else as the dynamic viscosity mu over the density. Well, that is a very important quantity in this sense. Why? Because we somehow can differ, for example, or get an idea if the viscous effects are negligible. And if the Reynolds number is high, we know, well, the viscosity is negligible, and there we speak from high Reynolds number flows, for example, with neglecting viscous effects. It's clear because the Reynolds number is this ratio between the inertia and the viscous forces, and so these viscous forces can be neglected. They are in the denominator, and if they are small, you get a high Reynolds number. A second important quantity is our flow laminar or turbulent? You know, flows are very complex, and perhaps the most complex description we need is when we are somehow in a transition between laminar and turbulent. Do you know at which Reynolds number you get the turbulent flow in the pipe? Do you remember somehow? I guess you heard it in a fluid dynamics course. Somebody has an idea at which value?
If I remember well, 2,300.
Yes, very good, very good. Exactly, exactly. Okay. And then you have to imagine when we look, for example, at really turbulent flows, yeah, you have Reynolds number up to 1 million or even higher. And then the big challenge is how to resolve all these turbulent scales when you numerically solve the compressible flow equations. Almost impossible, yeah, because, okay, but that is very important and gives us some idea how we can perhaps simplify our mathematical equations to model for our specific case. So that's the Reynolds number. Now we have the Mach number, and that is interesting because the Mach number is a ratio between the flow velocity, a characteristic flow velocity, yeah, and the speed of sound. So here we have already the relation between acoustics, acoustic waves, because they propagate with the speed of sound, and the flow velocity, which is the velocity of the particles, yeah? How fast they move on. And that helps us to differ between if we can model the flow as incompressible. Please remember we already had this in the conservation of mass. Incompressible, we can model that the divergence of our velocity is zero. Or we have to take into account compressible effects, and that is always the general case. We have a compressible fluid. And for this, we know that the mass conservation, and I write the mass conservation now simply in index notation, is that we have a change over time in the density plus, I told you it will be this part, plus the divergence, which is the derivative with respect to xi of the product density vi is equal to 0. Okay. And that is important. Actually, in order to have wave propagation, we need a compressible flow. But if the Mach number is small, well, to give you some numbers, so the speed of sound is about 340 meters per second. So it is quite high. And yeah, if you are within airplanes and you look there at the nozzles, for example, of the drives there, then, well, we are in a similar range. But if you look the flow around the car, even if you are driving 150, 200 kilometers per hour, you will have then for a Mach number which is beyond dot, which is about 0.2, 0.1 to 0.2. Do you know where is somehow the limit? What we very often use to say, okay, if the Mach number has this value, let's model it as incompressible, and if it is above this value, we have to model it as compressible. Do you have an idea? Do you remember from your fluid dynamics course? So concerning these two parts, incompressible, very often we say when the Mach number is smaller, 0.3, but be careful, that is just for a general case. You always have to look at your specific case, and compressible then if the Mach number is larger, 0.3. So this is a typical value used in fluid dynamics. Okay, another important quantity, dimensionless number, is the Struhel number. The Struhel number is extremely important for us towards flow-induced sound, because let's consider a very simple case. You have an obstacle here, and you have here a flow around these obstacles. Then perhaps, you know, we will get here vortices being shedded, and we have this so-called Kármán vortex street behind this cylinder. And what is here very interesting is that with this Struhel number, we get the relation between this shedding frequency. So F is our shedding frequency. L is the length scale. The length scale for our case would be, for example, let's say here this dimension L. We can also use the diagonal of this square cylinder, but this is the dimensionless the geometric characteristic length scale, and we have the velocity. So you see exactly when the Struhel number, you know the Struhel number, and that is for a lot of different rows within a large range of the Reynolds number constant, then we immediately can compute the shedding frequency, F, as you can see here, is the Struhel number multiplied by the velocity over the characteristic geometric scale. So we simply see if we have a flow around the obstacle, the shedding frequency is direct proportional to the velocity. So it fully increases with the velocity, and it decreases when your characteristic length scale, so the diameter, for example, of your cylinder is getting larger and larger, or it increases this frequency when the diameter of your cylinder gets smaller and smaller. And what is important is that this shedding frequency is exactly the frequency also of the acoustic wave. So it is not only the shedding frequency, it is also the frequency of the acoustic waves being generated, which are actually, that we will then also go into details, they radiate in this direction. Yeah, so they are more or less 90-degree oriented towards the flow direction. So this is the sound being radiated. So you see, this is a very important dimensionless number for us. Yeah, and then we also have the Helmholtz number. The Helmholtz number also relates here, as you can see here, frequency, length scale, and speed of sound, or simply, and that is the definition, the length scale, and please be careful, the length scale is the length scale of the flow, for example, the diameter of a vertical structure, and the wavelengths, lambda. Yeah? And the wavelengths lambda you can also write as the speed of sound over frequency. And we will see that this important dimensionless number tells us if, for example, our region is acoustical compact, yeah, that we will discuss, which would mean we have a very small source domain and the wavelengths being generated is very large compared to the vertical dimension of a eddy, for example. Yeah, so you have small vertical structures, and they generate waves with large wavelengths, and that would be typically at low Mach numbers. But we will discuss in this sense here. Okay, so we see these are the four important dimensionless numbers, where already, as we have seen here, 3 gives relations between the acoustic part within a compressible flow and the vertical classical vorticity part in a flow. And a further important dimensional number, the Reynolds number, gives us somehow the relation in this sense, if viscosity has to be taken into account or not, and if you have a high Reynolds number flow or low Reynolds number flow, if you have a lot of vertical structures, or it is going towards a laminar flow. Okay, do you have questions up now for this part? Or interpretations? Perhaps you also had some different physical interpretations of these dimensionless numbers. Okay. No reaction back, so I assume that this is understood by you or already well known. Okay, so let's come, before we go towards acoustics, within a flow, to this very important physical quantity, vorticity. The vorticity, I think, is one of the most important quantities within a flow to describe flow structures. And actually, we can, as written here, the motion of the fluid particles. We can decompose in three types, and that is the translational motion, which is typically within a potential flow, a rotation, which gives you the vorticity, which is we have in turbulent flows, and distortion of the shapes of your fluid particles, which indicates the strain you have within your flow. And the strains you introduce in the flow because a flow has a viscosity. So these are due to the viscous forces you have within a flow. And for this, we introduce the rate of the strain tensor, which we already have seen, which is here a general tensor of second order, which is non-symmetric. But what we can do here, because it's the gradient, as you can see here, of the velocity. So I could also write this as the gradient of the velocity. And we already have seen the gradient of a vector gives you a tensor of second order, which is not symmetric. But the important thing is we can decompose it into a symmetric part. So this is symmetric. And in an unsymmetric part. And why we do it? Because the nice thing is that this unsymmetric part can be associated to the vorticity. Because the unsymmetric part clearly, as shown here, gives you also a tensor of second order, but this tensor has no entries on the diagonal and has just 3 entries different from 0. And that you can rewrite in a vector, and we call it the vorticity vector. And you then can show that this is the same as taking the curl of the velocity vector. Okay, so you see, in this case, out of the rate of the strain tensor, from the unsymmetric part, we get the vorticity, and we can also rewrite it as the curl of the velocity vector. And the curl always gives you the vorticity strength in general speaking for any field. You can also have electromagnetic field. There you also have within Maxwell's equation the curl of, for example, the magnetic flux density. And this gives you also, we call it there, the vorticity strength of this physical field. So for example, the magnetic field is very similar to the incompressible velocity field in a flow, because there you also specify that the divergence of the magnetic field is equal to 0. So very similar as we have it here for incompressible flow, where also the conservation of mass is reduced, that the divergence of the velocity is 0. Okay, so this vorticity describes us the vortical structures, and therefore I should also write it here. This gives us the vortical structures of a flow. Okay, now the vorticity lines are always tangential to the vorticity vector. Yeah, so for example, we have here really such vectors. And the vorticity lines then are just this connection, and as you can see here, we have closed field lines, and that's typical the vortical structures we have there. If this is the case, yeah, and since this is a pure solenoidal vector field, so I should write it here. So the vorticity is a solenoidal vector field. Then if you take the divergence and integrate over a volume, you can rewrite it by the integral theorem of Gauss. So from here to here, we have the integral theorem of Gauss, that the closed surface integral of this quantity is always zero, which means the amount going into the volume and going out is balanced and gives you zero. Yeah, by rewriting the momentum conservation with this vorticity vector field, we come up to Crocos' form of the momentum conservation, which is quite different, as you can see here. I just have written it down. The derivation you can find in the script. And this is very interesting because on the right-hand side, you have once the curl and once of the vorticity and once the divergence, the curl of the vorticity and once the divergence of the velocity. So this term, the second term is already zero in an incompressible flow. If it is compressible, clearly it is not zero. In addition, we have introduced here this relation, and this relation gives you the so-called total enthalpy. So capital P is the total enthalpy, and you see it is a part where you integrate here the density, which has any relation. So sorry, not this. Otherwise you cannot do it, but the density will be any function of the pressure, which means you then can integrate over this term over the pressure. And the second term is just our kinematic energy we have normalized to the density. And also important quantity, which we will discuss in detail when we come to Aeroacoustics, is the lumped vector, which is given by the cross product between the vorticity and the velocity. Do you had already in some courses a discussion about this lumped vector? So it is, yeah, not so typical, I would say, when it is a classical course in fluid dynamics, but when you also discuss a little bit towards acoustic, that is an important quantity. And this vorticity is important because it is really the mechanism how sound is generated, and why this is so and this is so important, that there is also one very important theory, and you call it the theory of vortex sound. And we have a very nice physical model where you really can show how out of a single vortex you generate wave propagation, and so the vorticity in this sense is a very important quantity for aeroacoustic, but as you know also clearly for classical fluid dynamics. Yeah, and out of this incompressible Crocus form, so this was the general form we had here. Now, if we assume that we have a incompressibility, we can model a fluid as an incompressible flow, we come up to this part here, and that shows us that the total change of the vorticity is given by the first term here, which is a dot product between vorticity and the gradient of the incompressible flow. And the second term is just the vector Laplacian of the vorticity scaled with the viscosity here. And the first term here is the interpretation. So in the absence of viscosity, vortex lines move with the fluid. Yeah? So if you have a vortex tube, for example, this is also a typical tool to visualize the vorticity, to have vortex tubes. And if this is stretched, so the cross-sectional area, for example, is decreased, then this just can't be the case that the vorticity increases because the cross-section decreases. So this is the interpretation of the first term. And for the second term, yeah, this is a term which is extremely important where you have high shear. So near walls where you have high shearing of your fluid, because directly at the wall, the flow velocity is 0. And at these walls, due to the high shearing, you generate there the vorticity. So vorticity is generated at solid boundaries, and they are then diffused into the fluid domain. So that also tells us, well, actually this term, if your viscosity is small, could be set to 0, but from the physical point of view to understand how the vortical structures are generated near the boundaries and then they are diffused in the fluid domain, it is an important part. Yeah? So this is somehow you get more insight into a flow when you have this kind of physical models behind, even if we do there some simplification as we have done here. We have Crocus form of the momentum conservation for the so-called incompressible flow model. So incompressible flow without vorticity. Well, this is also possible, yeah. And as you know, we call this the potential flow. Yeah. If, don't forget the following, if omega is equal to 0, it means that the curl of the velocity is equal to 0. Now, if the curl of the velocity is equal to 0, you can rewrite the velocity by the gradient of any potential. In our case, it's the flow potential, because the curl of a gradient is by definition always 0. Just do this in the afternoon or evening and compute this explicitly. You will see, use Cartesian coordinates. You first compute the gradient of a scalar function and then take the curl. You will see that this is exactly 0. Okay, so you see that this is quite interesting. A potential flow has the property that the divergence is equal to 0, yeah, because incompressible flow means the divergence of the velocity is 0. On the other hand, the curl of the velocity is 0, so it is divergence free and curl free. And this is then the defining equation, as we see here, for the potential flow. In a general case, now we come to this part, we have the Helmholtz decomposition, and for any physical field, you can decompose a physical field into a vertical field. So this is a vertical field, vertical vector field, which you also call a solenoidal. Vector field. And you see, you can describe it by the curl of any vector. We call psi will be for us a vector potential. And perhaps to make it a little bit more understandable, since perhaps you had not so much field theory concerning Helmholtz, let's go here. And I write it again down. So we have the Helmholtz decomposition of vector fields. And that tells us any vector field, and I write it already for the velocity. It makes sense because we are discussing it for fluid dynamics, can be described by the curl of a vector plus the gradient of any scalar. I take here phi. Yeah? So this we call a vector potential. And this we call a scalar potential. And the curl of this, yeah, is again a vector field. Which is solenoidal. I write it here, you have closed field lines. Yeah, that is like a vertical structure. Yeah, if you show this, then they are looking like this. Yeah, as a vertical structure. So we call also this the vector field, which is solenoidal, and is a vertical field. So that we have now all the expressions in English, you call it solenoidal field or vertical field, and this is described. On the other hand, we have the gradient of a scalar potential, and this you call a irrotational field. A irrotational field means you have somewhere sources, and somewhere you have sinks or just one thing, and the field lines look like this. They go from the source somehow to the sink. This is an irrotational vector field and can be described by a scalar quantity as shown here, which is phi. Okay, so this is a general decomposition, which is for us important because at the end you know the acoustic field is a scalar field, yeah, but a pure scalar field, but the flow field is clearly always a vector field in this sense. So we need always somehow vectors to describe it. The acoustic field can be described by scalar, which is, for example, the acoustic pressure in this sense. Okay, so if we go back, then we can use now this information. So we can see that for an incompressible vector field, in our case, an incompressible velocity field, as written here. And I hope it's now working. Why is this not working? Okay, perhaps one moment. My pen is not going here. So let's see if I get it again. No. Okay, I use this one. And this is also not okay. So okay. Okay, very interesting. Okay, so I will just perhaps close it and reopen it. Hopefully it is then working, the PDF. Yeah, very interesting. So that is really this. Okay, I think we can let's make a break for 5 minutes, and I hope I can resolve this problem with my pen on the touch screen. It is working. No, it's also not working. Okay, now perhaps it's coming back. Yeah, now it's coming back. Okay, so the Helmholtz decomposition in the sense of an unbounded domain is as follows, as written down here, that we can decompose, as I have shown you just before, in a irrotational field described by the gradient of a scalar potential, which will be for us at the end such a potential flow, or if this is changing, then we even get the relation to an acoustic wave, and the curl of a vector potential, which we directly relate to the vertical structure. Therefore, our velocity v has an index v for vertical structure. So this is here for vertical. And now, having the properties that the divergence of the curl is always 0, or the curl of a gradient is always 0, we get the defining equations. When you look here on this equation here, and we take the curl on this equation, yeah, then we get here the curl of the incompressible flow velocity, which we have here, which is our vorticity. The curl of a gradient is 0. So what remains is the curl of this vector potential. Yeah? And that is exactly what we have here. Yeah? So you see, you get a partial differential equation where you can compute now this vector potential psi, and the operator is the curl operator, and it is driven by the vorticity. Yeah, that is of great interest. It's driven by the vorticity. Now, since the divergence of psi can be set to 0, you come up to the Laplacian of psi is equal at the end to the vorticity. And that you can rewrite somehow by Green's function as an integral, and then you get the estimate, and that is important for us in fluid dynamics, that the vortical structure goes to 0 as the distance goes to infinity, but what is important, with the order of 1 over the distance to the power of 3. So you see that the vortical structures decay very fast. And we will see that the wave structures decay by 1 over distance. Yeah? So you see that in most cases, and that is the good news for us in aeroacoustics, we can restrict the computational domain where we compute the flow, where we compute the vortical structures, which will be somehow the sources for generating the acoustic waves. And we have to compute the acoustic field in a quite larger domain, because there the decay of the amplitudes of the radiating waves just decay with 1 over distance. Okay. Do you have questions to this part? It
was fine. Thank you.
Just fine. Okay. Okay, that's great. So I hope you also now get a little bit the idea of this Helmholtz decomposition, and what is the irrotational field and the vortical solenoidal field. Okay, that's great. Okay, now, as I have told you, you will have no wave propagation if you have an incompressible medium. So you need a compressibility in a medium to have an acoustic wave, which means, for example, in vacuum, you will have no acoustic waves. Yeah? In air, we have a compressibility, we have acoustic waves. Now, this is a rewriting of the conservation of mass. Yeah. So as you know, this total derivative I could also write as following: as the partial derivative with respect to time plus V in nabla density. Yeah. And since we have divided by the density, we get exactly here this form. Perhaps I rewrite it a little bit, because then it will get, I think, clearer for you in this sense that I have to get back my notes. And let's start what we had. So what we had was, for the mass conservation, the time derivative of the density plus Yeah, I think that is not too large. It's better here. The time derivative of the density plus the divergence of density multiplied by the velocity equals 0. Now this term, since the Laplace operator is a linear operator, you can rewrite it as, according to the product rule, you first take the partial derivatives on the velocity and let the density constant, and then you do it on the density and let the velocity constant. So that gives you a first term, which is density divergence of velocity plus velocity dot product gradient of the density, which means we can rewrite it in this form that we have now the time derivative of the density plus this convective part is equal to minus the density divergence of the velocity. Now, if you divide by 1 over density, then you have 1 over density, yeah, and this part, you know, we can rewrite as the total time derivative is equal to minus divergence of our velocity. Okay, so you see this is nothing else as a kind of a reformulation of our general mass conservation, taking into account compressible fluids, which is for us important because we want to come up towards the description also of wave propagation. Okay, now with this additional information, it is now for us clear how we get this part here. Okay, now we apply a Helmholtz decomposition. Okay, now I have again the same problem, very interesting, in this annotator that he sometimes doesn't like. Okay, that's really strange that he has these problems. So I have to reopen it. And hopefully working. Okay, so that we have this Helmholtz decomposition. Okay, perhaps I have to synchronize it again. That's my pen. Okay, I think it's a hardware problem with my pen. I just put it back, wait for some seconds, and then perhaps he will resynchronize with the screen. Hopefully. Or it is really a problem with the annotator. Okay, at least this is working, then I can show you. Okay, so when we do this decomposition in the gradient of a scalar potential, now phi tilde and psi tilde, the curl of the vector potential psi tilde, and we put it into this equation here, yeah, then we have here the following, that we take the divergence of the velocity, which we have decomposed here in this part with this gradient of the scalar potential and the curl of the vector potential. And what we then get here is, as you can see, it is the divergence of the gradient of the scalar potential minus the divergence of the curl of the vector potential. Now, since the curl of the vector potential is always equal to 0, we get now a pure scalar equation for this scalar potential. And as we see, the scalar potential is driven by a change of the density. Yeah. So in this sense, we see that we just get this when we have a change in the density. And that is the importance that we have this. So again, the connection to the motion of a fluid. So the translational motion is a potential flow. The rotation is due to the vorticity we have within the flow, and compression of particles, for example, distortion of the shape needs compressibility. And that is why we can have a very general decomposition of the flow velocity in vertical parts, which will give us this rigid body rotations, in compressible parts, and into an additional velocity field where we describe this the potential flow, because the compressible part itself is described by a classical irrotational field. So we have here the distortion of the shape, and in this sense we have then three physical fields, where our vertical field is really the classical flow structures we have within incompressible flows, and the compressible part is decomposed in two physical fields, which we can both describe by two scalar potentials. Now, how can we come up here to the equations when we have this general decomposition and this connection to the motion of the fluid particles? So this additional phi here, which is our typical potential flow field, really solves for the Laplace equation. So you have no sources, so the right hand side is 0, but you have a boundary condition which is coming from the velocity. So the normal component of the velocity has this relation to the normal derivative of the potential flow on a boundary. So you have moving boundaries, for example. Then we have the classical vertical field, which we already have discussed, and this compressible part, radiating acoustic field, where we have classical here a boundary condition which is equal to 0, so it is homogeneous, but we have the sources, and the sources are coming from the divergence of the velocity field. Yeah, and we know that all the vertical structures cancel out here, because the vertical structures are within the vorticity, and the vorticity is the curl of the velocity and when you take a divergence, then it will be always equal to 0. So this is the possibility to do this full decomposition, and we will have there also some interpretation and description then within Aeroacoustics, where we use this very general Helmholtz decomposition, not only in a classical vector potential and scalar potential, but in a vector potential and two scalar potentials, in order to get also the physics in from fluid dynamics, where we know that we can also describe a part of a flow by a potential flow. All the vertical structures we just can describe by vector fields, which we also call solenoidal vector fields. Okay, so this was our first part of our course. Let's say a summary of the fluid dynamics equations, some physical interpretations to them, and then the very important results that we need a compressible flow in order to get also wave propagation. However, we will see that this will always lead to very complex numerical simulations, and it makes sense, according to this physical interpretation, to think for some special models in aeroacoustics where we can somehow separate the flow and the acoustic wave propagation. For this, it means we have to describe the flow up to some limit correctly, and on the other hand, get the idea how we can model the acoustic sources being generated by the flow, and then take these sources for a separate computation, and in most cases on a quite large domain, but there we just solve for the wave propagation. We have seen that the vertical structures, being the typical structures in the flow, that these vertical structures decay by 1 over distance to the third. So the flow and all the vertical structures will be always very confined in a somehow small region. However, waves propagate with an amplitude decay with 1 over distance. So you will also have the acoustic waves quite far away, for example, of an airplane. However, the flow is very restricted around the airplane. Yeah? And so this makes sense to then not solve the full set of compressible fluid dynamics equation on the whole domain, but just restrict this equation to a smaller domain, find physical models for the sources, which we can then use in a wave propagation model where we just solve for the acoustic field. Okay, so next time we will then just take our compressible fluid dynamics equation, make a perturbation ansatz, and we will see we come up to the general acoustic wave equation. We will just consider linear wave propagation, which makes sense and is mostly appropriate for all our models. And then we'll go in some details how we can solve this wave equation, what are typical wave structures, and how we also get simplifications and come up to very handy formula to have at least in a very short time an approximation what will be the acoustic pressure in the far field, and that will help us then to not fully start with all the very advanced numerical simulation tools to get out the flow and the acoustics, but first to get and understand the physics and have first approximates in order to have an idea how large, how strong the acoustic field will be due to your flow structures you have. And that was exactly also the ideas Lighthill came up in the last century. He was the first who really understood, let's say, aeroacoustics. And he also did a lot of analytical derivations to get handy formulas to know how, for example, the acoustic radiated sound power scales with the amplitude of the velocity. And that will be then the part, our last part, where we will try, since we then have all the equations from fluid dynamics, the idea about acoustics, that we combine this and find suitable models where you can also solve practical problems like the flow and the generated sound you have within air conditioning systems, or to how the sound is generated when we are speaking, so how the voice comes up, it is typical flow-induced sound, or the flow around the car and how can you compute there the generated sound. So these are all typical examples, practical examples, where you more or less will not succeed in practice when you try to solve the full set of compressible flow equations, because you will end up in so many unknowns that even on supercomputers you will not be able to apply them and get a result in a reasonable time. And reasonable means for me within, let's say, a month. For a lot of problems, like I have explained to you, just a ventilator or a compressor, turbocharger noise, and so on, very often you need at least 2-3 weeks just for the flow computation to have really reliable results with which you then can go into one of the models we will discuss and compute the generated noise, the generated acoustic sound. Okay, are there any questions so far? Or you think everything is clear? Okay.
For me, it was clear.
Yeah, that's fine. Okay, that's great. Okay, so in this sense, I think we should now, and for this I will go back one moment.